Hello, everyone. So this is really just an overview of our content programs, how we capture and produce and serve up the data. So there's quite a bit in there. I'm going to go through it reasonably quickly because I only got half an hour. There's quite a lot in there, and yeah, happy to take questions at the end. So I've got a few slides to start. So about game mapping. So our main competencies are the aerial survey services, and data hosting and mobile mapping. So I'm going to be concentrating on the first one for the purposes of this webinar, which is the aerial survey services and how they feed in and create our content programs. So I'm not going to do anything on the mobile mapping side. I've got a few slides at the end on data hosting, mainly on the aerial survey side of the business. Just a little bit about us. I don't know what you know about us, but relatively small company. We've got two main locations. So in the UK is where our head office is, down in Hampshire. And we, at the moment, have an aircraft base at Liverpool Airport. We also have an offices in South Africa, Cape Town and Centurion. And Cape Town, they do most of their aerial photography production. So a lot of what I'm going to talk you through outside of the flight operations bit is done by our team down in Cape Town. So that is us. I guess there's about, at the moment, there are about 20 of us in the UK and another 30 down in South Africa, about 50 in total across all of those locations. So the first section is going to be on capturing aerial photography, and there'll be a bit on processing. So I don't know how much all of you know about this. So apologies if this stuff you know, but I'll take you through it anyway, reasonably quickly, and I'll get on to all the products after that. So first few slides is really where the trends have been going in the last 25 years since we've been doing this, and the trend is to larger cameras. So we started capturing photography in 1999, back when everything was analog. And then the first digital sensors came along in the early 2000s. We were early adopters, and we've been with them ever since. So the trend since then really has been to improve CCDs. Two things. The first thing is increased overlap, and the other one is increased footprint size. The footprint is the area on the ground taken by one image. So that is drastically improved over the last 20-25 years. They're packing more pixels onto CCDs. The technology is better. Response times are better. All of that drives a few things. So the first thing is that you can reduce your flying time. If you've got bigger footprints, you need to take fewer photos to cover the same area on the ground. And that is improved update cycles of all of the imagery. So now, when we started, it was 5 to 7 years updating the UK. Now we're down to 2 to 3 years to update the UK. So that is a really big improvement, and obviously that's been driven by demand for content. The second innovation really is a faster camera cycle time. So this is the time it takes for the camera, how quickly it can take photos. The quicker it can cycle through photos, you can fly at a much higher overlap and a much faster speed. And that really helps when you're flying lower to the ground. So they're the big innovations in terms of the technology. We use large format cameras. So Getmapping, we have got different cameras for different altitudes. So we've got ones that can capture at 19,000 feet, the 12.5 centimeter data we capture nationally, which gets us above a lot of the really tricky airspace, especially above London and the big cities. And obviously that's a really big factor. So we have kept up with technology. We've got the best of breed cameras. And we've got a variety of lenses to to enable us to fly in different parts of the country where there are different challenges, especially for airspace, and also, yeah, especially above cities where they are very specific and increasingly so where you are able to fly and where you're not able to fly. So again, camera choice is a really important factor in getting content programs done. So all of our cameras, Google XL, you may have heard of, they are sort of the market leader. So we've always been with them. All of the data is captured with red, green, blue, and near infrared at the same time. So all of our production flow line is in 4-band imagery, which I'll talk about that a bit later, but it means that everything is synced up, all of the bands, and it's captured at exactly the same time. And finally, on technology, again, aircraft choice is also really important as well. So content programs, you are wanting aircraft that are able to fly, with a decent range. So you're up in the air, you need to maximize, especially in the UK where the weather isn't always that great. You need to maximize all the opportunities that you're given. So, you want a decent range on the aircraft. And again, there's a choice of pressurized and unpressurized aircraft, and you choose that according to what altitude you want to fly. And that's also linked to airspace and what projects you've got. So again, along with camera choice, aircraft choice is really important. And we're lucky we've got available. We rent. The general model in the industry is you rent in. We don't own aircraft, we rent them in. So we've got a partner at Liverpool Airport who can provide a range of aircraft to suit a range of needs, of which these aircraft types are good examples. So yeah, I think it's, as sort of the summation is, for content programs, there is increasing demand for more updates. There's increasing demand for higher resolution data, and therefore you need to keep up with technology, both for cameras and aircraft, to enable you to deliver those content programs. So the next section is production. So I've got a few slides. Really, I'm not going to take you through a deep dive on how we produce stuff. It's really the themes that we have in our production, which are the requirements for our end products. So again, one of the main things that is really important and increasingly important is overlap. So we fly with a really, really high overlap, and the increased cycle time, faster sensors, bigger footprints enable us to fly with this very high overlap. So the reason for this is that we, as you'll see when I get down to the later slides in the production, we fly with an 80% forward overlap and a minimum of the 30% side overlap. And this is really the minimum requirement for creating data where we can actually derive height data, DSM and DTM, from the aerial photography. You need all that overlap. So we fly east-west or north-south, and again, it's working with air traffic in those areas to place the flight lines in the best position to give us a chance of capturing, especially in busy airspaces. So again, it's I've done this slide before. Again, UK, this is an animation of weather over the UK in one flying season, and it's really variable. So you do need to maximize every opportunity, which is why there is a trend for taking bigger and bigger sensors, bigger and bigger footprints, because sometimes, as in this summer, good weather is really hard to come by. So you need clear skies, and also you need the correct sun angle. So we fly, there's RIC specs we fly, which determine things like minimum overlap, minimum sun angle, accuracy, orientation of the aircraft, all those things, the inputs that make sure that your outputs are hitting all of the required project specs. So that's kind of the flying side. So once we've flown the data, obviously there's a process to produce the photography. So again, one of the main things we need to look after is accuracy. So the all of the flow lines are there to absolutely maximize the accuracy of the data. So we have what's called a GPS and an IMU. So the IMU measures the angle of the aircraft relative to the ground, and obviously the GPS measures the XYZ position. So again, there's a phrase, it's the law of marginal gains, aggregation of marginal gains. So all of these little marginal gains in accuracy are needed to make sure your outputs are as accurate as possible. So this is accurate GPS, really good IMU data, all of that really high overlap, and that leads into the accuracy of your aerial triangulation and your the accuracy of your output data. So we need all of this to be as absolutely accurate as possible. I could probably go in deeper if I'd long to as to how we do it, but I won't do that now. So again, one of the increasing trends of software is becoming increasingly sophisticated at processing color. So you're taking a series of individual images taken over the course of maybe 2 or 3 hours, varying light conditions on the ground. And there's a lot of really good algorithms now in the processing software that can even that color out when you're stitching all your images together in an ortho photo. The color looks real and everything is seamless. So there is, again, there's been a lot, and there is ongoing innovations on the software side that handle things like color and radiometrics to improve the color as much as possible. And I think we're seeing where we used to see, for example, flying over big cities. London was a bad example where air pollution seems to be getting worse and image quality seems to be getting worse. So you're going to need more to overcome that on the radiometric processing side. So this is, again, it's a very important thing to keep up with software and innovation to make sure your data is evolving and keeping being as good as it can get. So that's one side of the processing is radiometrics and color. The other one, feeding from your GPS IMU data, is aerial triangulation. And again, this is now taking advantage of computing power. So going back to our really, really high overlap, we're flying with an 80% overlap along a flight line from frame to frame, 30% side lap. What the software is doing is now creating hundreds and hundreds of thousands of tie points generated by the software, and then with strengths of connectivity, and then we're adding ground control points, so known survey points of a 2 to 3 centimeter accuracy, which are the green triangles on there. And you're throwing all that into the mix with a massive amount of computer processing power. And what the software can do these days of aerial triangulation is give every pixel in your data set an X, Y, and Z value. So that's every single pixel, which is a really powerful thing because the first thing you can do, it can create a raw DSM at the resolution you're flying at. Which is it's a really good output, straight derived from your aerial photography. So this is, and it's not perfect. The quality of your DSM is directly linked to the overlap and the flying conditions. And if you're thinking you're in an aircraft flying over a bumpy surface in a very turbulent environment, there are going to be places where your connectivity is better, some places where it's worse, but actually the output at this point is very good as a starting product for a surface model. So that's one thing we can produce straight out, and as a starting point, you can edit. I'll get to that a bit later, to create an edited DSM. So that's the first output from what's called the dense matching process. So every pixel having this 3D element, and a very, very high degree of accuracy, thanks to the accurate GPS IMU and that high overlap. So what that enables us to do is, when it comes to orthorectification, so what is orthorectification? That is creating a flattened 2D image projected to whatever your mapping projection is, from 3D data. So if you can use a DSM, traditionally you'd use a DTM, you'd import in a DTM to do orthorectification, but now we're using a DSM, and it's the DSM generated by the imagery, and you've got so much more information that the computer software can use to flatten the imagery. And what that does is take out things like building lean. I'll show you some examples a bit later. So again, we're now using the DSM to orthorectify the imagery, because this is enabled by increasing processing power. So that is another innovation that the technology has enabled us to do. So that brings us through to what are the products we're producing, which you're hopefully going to be familiar with. So core data sets, we can output 3 or 4 band orthorectified photography, and then directly derived from that photography is the DSM, which we edit, and then from there you can edit out a DTM. Again, it's worth mentioning that our ortho-photography flow line, everything is done in 4-band. So if you remember, the camera captured red, green, blue, and near infrared at the same time. So we retain that through the entire production process. So our output is actually RGBI images, and then for the products, we can just split out the bands in GDAR to create RGB or CIR images at whatever resolution is desired. So looking at the ortho-photography, again, this shows the difference between using a DSM and a DTM for orthorectification. So on the left is a standard ortho using a DTM, and again you've got building lean in there, because the computer hasn't got all of the vertical information on the ground to know. And again, it's probably flown with a lower overlap as well, so you haven't got as much information to actually work out the most vertical pixel and position of pixels when flattening into 2D. And then on the right is a DSM ortho, what's called a true ortho. So again, the advantage of that is that if you're using it for any topographical mapping applications, you're not going to be missing detail on the ground. So again, that's a really big advance, which we've seen in the last few years. And as I mentioned, we've got RGB and CIR, so everything is produced in RGBI. So the RGB and CIR are temporarily identical. So any edits we do are all done in RGBI. So you are everything is exactly the same. And again, if you're going to be doing any sort of analysis on the data and DVI or anything like that, vegetation analysis, you're going to need everything to sync up. So again, all of our imagery nationally is RGBI, so RGB CIR are identical. So they're the products, the ortho products, and again, the ortho content programs, we've got 2 strands now at the moment. So National View, we have a full UK 12.5 centimeter data set, which is called National View. So we've got that in RGBI, and we've also got that in, we've created a CIR one as well. So that's on the right. So again, you know, you've got full coverage at a very good resolution nationally. All of our National View data is newer than 2021. And now we are with, again, new cameras, better aircraft. We are now starting to build up our city view data, which is 5 centimeter data of city centers, or major towns and cities, not just city centers. So we are working our way around the UK, capturing 5 centimeter data of cities. So again, looking at the city view, it gives you really good resolution of still quite big areas. You know, obviously it's urban focus, it's where most people live. And again, if you're looking at accuracy, the accuracy is related to the resolution you fly at. So again, you know, you're looking generally at about 3 pixel accuracy, 2 to 3 pixels. So you're now looking for 5 centimeter data, you know, 10 to 15 centimeter accuracy. So it's really accurate data. So, you know, what are people using the city view data for? And a lot of it we're looking at, you know, it's asset management. So we've got examples of, you know, people are able to have a look at, for example, the state of repair of roofs. You get huge detail, much better than you would get for the 12.5 centimeter data. And in some areas, you know, much better than you get in most data sets. It's really high quality data where it enables you remotely to have a look at your assets, the quality of them, or, you know, what you've got in your assets. And it's, you know, it's a really powerful data set. And again, if you go back, it's got, you know, you can see street furniture, road markings. It's got a really high level of detail. And then we've got, at the moment, we've got about 40 cities in the UK flown until the end of the 2024 season. So the 24 data is currently in production at the moment. So we're starting to build up, you know, a good library of 5 centimeter data throughout the UK, and that's an ongoing program. And then obviously we've got the National View, which is, as I said, yeah, full UK, 12.5 centimeter data, still a really good data set, still very high accuracy. Again, you're still looking at your 2 to 3 pixels. And again, from this, we are also updating our height data sets as well. Alongside, you know, we've got the National View current layer. We've also got historic data. So we've been capturing since 1999. So we have now built up a really huge library of air photography. So which is obviously really useful for any sort of change management. So again, we've got a vast amount of data available. So that's quite quickly on the ortho products. And then final section on products. So we can, you know, directly output a very high resolution DSM from the ortho-photography process. And this we can edit. So the DSM will need editing to flatten things like water, remove any artifacts and spikes. And again, we can do this at whichever, you know, resolution is desired by the market. So at the moment, we are doing a 2 meter National View DSM resolution. That seems to be a sweet spot for what most people need at the moment. But, you know, we are looking at now, yeah, what can we output? So for our 5 centimeter data, we can actually output a 5 centimeter DSM, which is hugely accurate. It's a massive data set. It's a lot of data. It's about 1.5 gigs a tile, but it just shows what is possible. So that is something we could serve up and productize, edit. So there's a lot of possibility with the 3D data on the DSM side. And again, obviously, if you've got a DSM, then you can edit that and update it as a DTM by removing all buildings and vegetation for all its normal applications, flood modeling, etc. So again, we are maintaining a 5-meter DTM, so we're just updating that at the moment for the whole of the UK. So they're the main data sets. You can see I'm getting close to the end of my time, so sorry, this has been very whistle-stop, but I've just got the final few slides on serving up data. So again, one of the big things we've been at the forefront of over the year, I mean, since we've been doing this, we were early pioneers of managed data services, web streaming. So again, this is a really important part of the business. And again, it's really getting people using the data via WMS, WMTS, WFS. So we, again, have a lot of customers who access our data through this. Obviously, the bonuses are, you don't have to worry about updating your data. That gets taken care of you. And again, we've got really, really fast connections. So our systems were actually built 20 years ago when bandwidths were really, really much lower than they are now. So the technology we built back then has stood us in really good stead for when we've got increased bandwidths and we can serve up ever more complex data sets, higher resolution data sets ever faster. So we've got a really good core of web services. All of our data sets going back to 1999 are available to stream over the internet in WMS, WMTS, and WFS. So again, that is a really, really powerful tool for all of our customers. And I don't know whether EDINA users use it this way, but that is where we're trying to get people to consume the data. So that is my last slide. So apology, that is a real whistle-stop whiz through. I've done it in about 30 minutes. So happy to take any questions.